Yeah.
Eat microphone.
Yeah, I will eat the micro. Thanks. I hope it will get a little more serious than the video before. Thanks to Anne for having us here, and thanks everybody for staying. I'm Philip, this is Timo. We'll be talking to you about 3D concrete printing at architectural scale, specifically for staircases. Little context, our company is 5 people, and Timo is an integral part by now of it. He's not in our company, but he's helping us a lot. We couldn't have done it without him. And we are producing, we have invented a new 3D concrete printing method that's based on the particle bed. Printing 15 cubic meters, we developed the printer, we advanced the technology, and we sell the pieces that we print for customers. Here you can see the dirty business that it is sometimes. Getting freeform pieces out of there is like archaeology, but I'm just going to set the tone a little of what this technology is capable of doing by showing a couple of projects that we realized so far. For example, the one exercise that every 3D concrete printer has done is a pedestrian bridge. We've also done it, but it's 21 structural pieces that we found using graphic statics to have a compression dominant form. Then, to my belief, we've also produced the first consecrated, sainted 3D concrete. I don't know if it's true, but I guess it is. I hope it is. Just the method of installing that statue didn't speak for it being a saint. We had to hang it from the ropes. But I think the priest of the community would not be so happy of me showing this. So here you go. It's a little inside. And then here you can see the freeform capacity that we have with this method. And one thing that has been for us to go into the AEC industry are stairs, because it's a low entry barrier. And now we get our client showing us what they want to do. It looks usually something like this. We have to adapt to it, come up with something like this. In between is our fabrication method, and to the point that Timo got in between there was me getting slightly upset with my computational design workflow. So now we have Timo, and I can sleep well again. And I'll hand it over to Timo to explain why I sleep well.
Thanks a lot, Philip. And now we are last day, last session, so we're going to keep the questions a bit simple. What is a stair? So Philip came with these crazy-looking stairs to me, and like, how can we automate this modeling process? Is this one here?
No, it's that one.
Ah, that one here. So I took a step back. I was like, what is the minimal input you can give to create a freeform staircase with full design freedom? So we gather a list of ingredients for a stair. One set of ingredients is the boundary conditions. You have a stair starting one place, ending another place, and you have it starts at one side, stops at the other. So that's a very three-dimensional boundary condition. Then I like what a colleague in the field suggested to me. He was like, everyone can draw 2D, but no one can model in 3D. And I believe it when I see a lot of people's 3D models, including my own. There are often a lot of errors in them. It's much easier to model in 2D. So another ingredient to a stair, we can project it to 2D. We have a movement curve where you're walking up this stair, so a planned projection of a curve. We have the shape of steps. You can also draw those in plan. So it looks something like this here. Then you have the profile of the stair. You can unfold a spiral staircase, again, to a planar surface and draw the profile of the stair. And a natural calculation from that is good size steps that we then auto-generate. So now we have these two-dimensional ingredients, and from that we can build these like stairs that look like this. This is not the full stair, this is a stay-in-place formwork. So we come afterwards, put rebar in, pour some concrete in, but the formwork is what we produce to install these stairs much faster. Also, it gives us freedom to do any shape of stairs, spiral staircases, straight staircases, any architectural idea anyone might come with. So this is what we have now. It works nicely, but a year before this, my question was like, how are we gonna model this? How are we gonna represent this geometry? Because it's an extremely complex geometry to actually model. So I had a chat with this guy doing glasses, and he showed me how he is working with meshes, like rough meshes with very fine vertex control to have an extremely precise modeling of each individual point of a geometry. I was like, okay, we're gonna go with meshes for like a good control. So that gives us something like this. We take our ingredients, we apply an algorithm in Grasshopper, and we get this shape here. And this is fine for preview, but what goes to the printer in the end looks something like this. So we're still quite far from that, and we do need solids for our 3D printer. So we go a bit further with our meshes. We want these sharp edges somewhere, but we also want soft edges. We want to be able to fillet corners. We want to control where it's soft, where it's sharp. And here meshes are quite bad. There we actually like NURBS. So we go a step further, and we convert our mesh to a SubD. And if we have very fine control over our mesh, we can also control our SubDs very precisely and get perfect fillets where we need them, as long as we have good mesh control. So I just show them next to each other here just to show the difference. Like we maintain sharp features and fillet where we want fillets. So now we have this slide here, which is still a bit far from a staircase. We want something like this. So when we go on site and put this thing up, it looks something like this. So we have these boards that come in. We need to attach these boards to something so we can cast the concrete. So we need some detailing. So what you actually produce, what we print, is what you see over here to the right. Can I just go one? Yeah. So what you can see here is like all these what we call stringers are auto-generated in this case, and we use those to basically attach our boards on site. But I can automate the generation of these, and then you get something like this to the left here. But this may not be very good. It may not be a very nice way of working. It's a minimal number of stringers, but I know that Philip may prefer a different design. So here we use Rhino Grasshopper, but placed a UI on top and made sure that any type of automated output is also something that you could manually modify. So you can actually get the layout of stringers that is more efficient on a building site, which is extremely difficult to automate. So we have these shapes. We have our nice SubD representation. We have our stringers. And as a Rhino user, I will just want to merge all of this together. But Boolean operations, when you work with meshes and B-reps, is a nightmare. I'm going to get back to this. Because these are all our positive shapes, all the things we want to add together, but we also want to subtract shapes. So you see, this is a printed product. We have these areas where we have removed material. And what is the material we want to move? If we look at this here, like that's a section of a stair, we need the top. Like that part we don't want to remove. We also need the bottom, and we need this section here between the steps. And I'm like, okay, how am I going to model that in between part? So I'm a very explicit modeler. I work in Rhino Grasshopper, and I'm like, this is not explicitly defined. If there just was a way to implicitly define this geometry, something that NTOP does very well, Rhino doesn't really have that capability natively, but we used an isopod by Daniel Piker, which is an implicit geometry engine inside Grasshopper. So that allowed us to basically define our geometry as its distance to other geometries. Like it is an implicit geometry, so let's use an implicit engine. So that gives us these odd-looking blobs that exactly satisfy this requirement. So here I just show the positive shapes with gray and the negative shapes with red. And then we get back to this one here, because now we want to both add shapes and then we want to subtract shapes. And that brings us to the next geometry definition, because we then convert this definition to a volumetric model so we can do robust Boolean operations. So this is where we use an OpenVDB implementation called Dendro, also running inside Rhino Grasshopper. We take all our positives, we take all our negatives, and then we start by just running a test with a very high resolution of voxels. So volumetric modeling is voxel-based. So to begin with, we get this very rough mesh here. But what resolution should we use for our voxels? The higher or the finer we make the resolution, the slower it's going to compute. But we just need to have a resolution that is a little bit finer than the printer resolution, and then we're good. So we did that. And then we go from this to this here, and then we are actually ready to print. Though we do have a staircase that may be 8 meters tall, and having a voxel grid of 2 millimeter resolution and 8 meters tall starts to eat a fair bit of RAM on a normal laptop. So what we do is we divide the stair into different sections and then simply process them one after the other. So increase computation time, but it means you can run it on a normal laptop without running out of RAM. So just to summarize this little story, we start with simple 2D input. We generate a 2-dimensional mesh, or 2.5-dimensional mesh. We convert that to a solid mesh. We convert that to NURBS, so we can get the smoothness. We then use implicit modeling to get all the shapes we can't define explicitly. We convert it to a voxel-based geometry to then finally convert it to a mesh that we can send to the printer. We could also skip the last step and simply just calculate slice by slice. Would also be an option. But for now, this here was the way we went. And then I give it back to Philip.
Thanks a lot, Timo. So yeah, now we have all of these pieces ready to be printed, and we need to assemble them virtually in our build volume, which, as I said in the beginning, measures 4 by 2.5 by 1.5 meters, so equaling 15 cubic meters. And the printing method, as I said, is based on the particle bed, where we have this surface of aggregate, and our main invention, or the main technological advancement, is the printhead with a couple of hundred individual nozzles that inject the cement paste. So we have this cement paste pre-mixed, and it's intruded because it's called Selective Paste Intrusion. So it selectively intrudes the cement paste, then moves up 3 millimeter and applies another layer of gravel. So it's like laser sintering, for example, just without the energy of the laser, but cement paste. And as we continue, we're printing 15 cubic meters in 6 hours. One person can do it, and this is what it looks like in reality. So this is our plant in South Tyrol, Italy, where we develop these machines, where we provide the printing services, and where we continue to try and optimize this technology more and more. Yeah, so here's the cement paste being intruded into the particle bed, and then eventually, once you open flaps at the bottom of the printer, you can very easily excavate all of the pieces and take them out of the constraints of the build volume. Oops, sorry, too quick. And then here I come back in, I take my pieces of the stair, I move them on site. They're being lifted into the construction site, into the stairwell. We've optimized them over the last couple of years, since stairs were already in the history of the company. And it's actually quite a pleasure to install them, because everything is so precise. This was in Switzerland. Okay, to be fair, I've bribed them with lunch, so they were quite happy anyway. But it did work well. We installed one staircase in a single day. We also printed the parapets to make it to take away some or optimize this process. Also, make it quicker. We didn't need a mason anymore. Yes, and then once all of the pieces are installed, here came our German engineer that completely over-engineered the reinforcement that was necessary, but at least we were sure that this second staircase that we ever built will actually remain there for quite a while. And then comes the in-situ concrete. It's a fairly easy and graspable method of doing it, but the intention was to actually get this technology out there and build something with it, so people think it's a credible technology and it remains. And then what is very easy with this technology is the finishing of the surface. You can just directly apply it on the, although we would wish for someone that would actually expose the surface of the nature of these layers that are created while printing. The result looked like this. We were really happy with it. The Swiss people were also very happy with it. The owner too. It's been a 2-story staircase spanning around 8 meters, as Timo already said. And it's been featured in magazines in the EU. We're very happy to present it here now too. And this was another example that we did also in Italy. This is not a render, this has been just plastered over with the exact same finish everywhere. Yes, and that is one part of our business. We've sold these staircases far. We would love to sell more, but in the meantime, the brutal truth is that we make money by doing stuff like this. So we would really love to move on from design objects to more serious use cases of this technology, because it does produce construction-grade concrete, and we want to move on to producing walls, we want to move on to producing houses, we want to structurally and thermally optimize the parts that we print with it, because it is capable of, the technology is capable of doing that. So if you are interested in this, if you are from university, if you are from practice, we would really love to get your feedback and know where you would see this going. This is why we put a QR code here. You can simply scan it. Timo came up with the idea you scan it. There's an email prepared with a subject with our email as recipient, and we would be very happy to spam you. So yeah, that is it from our side. Timo, do you want to?
Yeah, I just want to say, any good ideas for anything you want to print? Talk with Philip. Any funny ideas of geometry that needs some automation? Talk with me.
Thanks a lot.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.